So, good afternoon students, this is the last lecture of our course and today we will continue with the problem solving that we started off in the last meeting. So, today I am going to talk about some correlation function that you can compute for the system of fermions in quantum, these are quantum systems. So, one would like to know how we deal with fluctuations of occupation numbers in a gas of fermions for example. So, let us recall a few things. So, we will talk about simple correlations and I would rather call them as moments and fluctuations, and these moments and fluctuations can be very easily used to construct correlations of the occupation number. Okay. So, I will start with the simple case and you can extend this to the case of bosons as well. So, for fermions, if you recall, these are systems with half Redinger spins and we know that their statistics follow the Fermi-Dirac rules. So, if you recall the average occupation number of any level I here is a single particle state, and if I am interested in the average occupation number, we know that Ni can be 0 and 1 for fermions, but the average Ni is not 0 or 1. So, this is computed as 1 over e to the power beta E I minus mu plus 1. Okay. So, as you can tell that at 0 temperature or 0 Kelvin, when beta goes to infinity, for any energy level which is less than the chemical potential at t equal to 0, and chemical potential at t equal to 0 is nothing but the Fermi energy. The occupation number is 1, the average occupation number is 1. So, if I sketch this occupation number at t equal to 0, I would get something like this. So, there would be somewhere a chemical potential at t equal to 0, this is a value on the x axis, this is also the Fermi energy, and everything below this Fermi energy would be occupied as 1, and this is where the graph would abruptly come to 0. Okay. So, if you are interested in for example, at finite temperature, if you want to compute some correlation or moments of the occupation number, then we would be computing variables such as we will be computing functions such as these moments, and I would like to just highlight why these moments are useful here. So, for example, you may be interested in computing the joint probability density of finding a fermion in level I and another fermion. So, this joint moment Nij is a joint probability of finding a fermion in the single particle level I and another fermion in the level j. We have taken this convenient assumption that I is not equal to j. Okay. So, we are talking about different single particle levels, and we are talking about the probability of finding one fermion in level I and some other fermion in level j. Okay. And this can be computed. So, this is a relevant question, and this can be computed by this joint moment n I n j. So, moments are important here. Okay. They give us some physical picture of something of some importance. Okay. So, immediately I know that the joint moment is important, and so we would like to compute that. So, let us compute this joint moment. Okay. So, if you recall, this joint moment is nothing but the it's nothing but the expectation value of n I n j. So, these are two variables n I and n j, and suppose I sum over all possible microstates and sample the n I n j. Okay. This is the variable whose average is required in the distribution, which is given as e to the power. So, this is my probability distribution. I will take a different variable here, let us say k, which goes from 1 to infinity, n k e k minus mu. Okay. So, here this variable will go from 1 to infinity, because we have infinite energy levels, right, and naturally this has to be divided by the norm, which is the which is our familiar partition function. So, I am going to write down once explicitly, but very soon I will be writing it with symbols. So, this is basically okay, where this entire denominator is basically the grand canonical partition function. Okay. So, this is like let us write this once more, and I have just made a small mistake here. So, this is summation over all the possible microstates, set of ni's, okay, that is my microstate, my variable n I n j, the product of two random variables, e to the power minus beta divided by my grand partition function. Okay. So, you can see that this can be written as if you look at the numerator, this looks like the derivative of my partition function with respect to the variable n j and n I. So, this is like a twice derivative of the partition function. So, this is like 1 upon q okay. So, the innermost derivative can be easily replaced by something that you already know. Okay. So, let us replace the innermost derivative as, so by the definition of average occupation number, this is nothing but so I know already that my average occupation number, which is n I, is given as 1 over q d over okay. So, which means the bracketed object in under red bracket is nothing but q times n j, average occupation number of the jth single particle level, q times. So, this is the bracketed thing. So, let me remove the, so that we know that the red bracket is replaced by a new red bracket. Okay. sort of homogeneity. All right. So, now this basically simplifies very easily. So, you can just write down by using chain rule. So, the first term would become if you apply chain rule straight away. So, this would become the derivative of the partition function times n j plus 1 over q the derivative of the occupation number, average occupation number times q. Okay. Of course, by the definition that we have written earlier here, you can substitute for this first term as expectation value n I into what you have as a remainder expectation value of n j, okay, and realizing that this q knocks off with this q, okay, but what you have is basically a derivative of a function. So, average occupation number n j is nothing but 1 over 1 plus e to the power minus beta e j minus mu. Okay. So, this has to go to 0 because the function does not depend on E I and you are taking derivative with respect to E I. Okay. So, this derivative goes to 0 and what you are left with is just the fact that these cross moments, if I and j are not the same, is nothing but the product of individual moments. I am sorry, so I must correct myself here. The cross moment is equal to n I n j. So, that is the first result. So, let us sort of save it. So, this is like the two random variables which are independent of each other, and so the joint moments are nothing but the product of independent moments. So, at some level you should have seen it coming because these variables are uncorrelated or independent of each other. So, some of you may say that I expected this because I know this from chapter 1 on probability, where we have computed cross moments of random variables that are mutually independent. Fine. So, if you realized that this is nothing but a revisit to chapter 1, some of the problems, then you are on the right track. You have been reading well and doing your homework well. Another thing that you can compute very easily for the fermions is the fluctuation of the occupation number. Okay. So, at t equal to 0 you can see there is no fluctuation all the way to the Fermi surface because the average occupancy is fixed, but at finite temperature you should expect to see some fluctuation of the occupation number near the Fermi surface, where the numbers will deviate from exact 1. So, let us compute the fluctuation of the occupation number. This is again something which is very simple to calculate. So, if I want to compute, so this was the first task, and if I now want to compute fluctuation of occupation numbers, so this would be like a second cumulant of some ith second cumulant of the occupation number of ith level. and we know that the second cumulant can be computed as second moment minus the square of the first moment. Okay. This is simply variance, basically simply variance of the occupation number Ni. So, we can compute this very easily by simply writing down the right hand side. Okay. So, the left hand side is basically this, and if you recall the definition of let me just remove this here, and so bring up the definition that is written here. So, we can simply write it here. So, recalling that the average occupation Ni is nothing but summation over all the microstates. Okay. And if Ni confuses you, we can take it as Nj. So, how about taking a different symbol? Okay. So, we can take a different symbol. So, average occupation is nothing but sampling Nj in our distribution, which is over the partition function. Okay. So, then you can see that I can write down the right hand side. Okay. I can write down this term, the right hand side here, very simply as so let me write down the left hand side first, and so the second moment is now very easily seen as 1 over q, the second derivative with respect to the jth level of my partition function minus the square of the first moment, which is basically the first derivative. Okay. And just a simple rearrangement of terms is required here. So, what we can do here is to see for the fact that I can write it as d over so we have been doing this many times now. So, you can write this as d over t e I, the second derivative basically of ln q. So, as you can see, the innermost derivative sort of expands to okay. So, let us sort of explain this what is going on. So, the inner derivative expands to 1 over q d over d minus beta I of q. Okay. And the outer derivative will give you the first term, which is this, plus the second term, which is this. Yeah. So, this is now fine. Correct. So, there is a typo here that I have to correct. So, these are both the derivative with respect to E j. Okay. So, I have corrected that typo. So, as you can tell that if you take one more derivative here, you will get your right hand side. Okay. So, here you can see that this is nothing but by the definition of average occupation number, this is nothing but the innermost derivative is nothing but average N j. Okay. Because we know that the average N j is nothing but 1 over q. This I think I have already written it here. So, I can simply ignore all that and okay. So, this is nothing but average Nj. Okay. And this we know that is nothing but by Fermi-Dirac statistics, it is e to the power e raised to beta E j minus mu plus 1. Okay. So, let us then proceed with our final calculation. So, this nothing becomes nothing but if I use this definition. So, this derivative can be written as e to the power beta okay. The 2 minus sign becomes positive. And so, this is let us not forget for the fact that this is basically the second cumulant of occupation number, okay, right. Which one? Yeah, that is what I have written, no. Oh, okay, okay. So, yeah, this is absolutely right. Thank you. So, this is the second cumulant, okay, and by substituting the value of the the first for the first moment, I can easily see that this is nothing but e raised to beta E j minus mu. The denominator is nothing but simply N j square, because that is what is written here. Okay. So, the square of this is nothing but N j square, but I can also replace this. So, I can also replace for e to the power beta this exponential, I can write this as so I can write this as 1 upon N j minus 1, right. Okay. So, let me write it here. This becomes okay. So, in terms of the occupation numbers, you have a neat closed expression which is N j minus N j the square. Okay. Is that fine? Right. So, I can also write down in terms of energy. So, this is the expression that we have obtained. So, let me this is an important result. So, let me just put it inside the box. So, this is the cumulant second cumulant of the occupation level occupation number, and it is obtained in terms of the occupation number itself. Okay. But suppose I want to write down the second cumulant in terms of energies. Okay. So, if the task is to write down the second cumulant in terms of energies, then that is also possible. So, you would like to set this up, you construct this, plot this as a function of energy. So, you can also write this as the second cumulant as, if I go back and pull down the expression somewhere here, yeah, it is here. So, I can use this to write it in terms of energy, a compact form, this can be compactified. So, let us copy it from here and take it downstairs, and if I bring it here, I can do something with it, compactify it, and yeah. So, I can do something with this, write it in terms of energy. So, realizing for the, I can just rewrite it. So, what I will do is write this as e to the power, the numerator I am going to write on as e j minus mu by 2 into e j minus mu by 2. So, I am writing the numerator like that, and I am writing the denominator as just write down the square as as a product of two factors, okay. And now just multiply by the inverse of the numerator. So, I will get a 1 there, and each of the numerator factor you divide it in one of the factors in the denominator. So, what you will get is basically e raised to minus so, what you will get in the denominator is basically the whole square, okay. So, this is this can be readily converted into cosine hyperbolic. So, what I have to do is basically now what I have to do is basically take multiply the numerator by 4 and denominator by 4, and simply remove this thing from here, or let it be like this, we will just write it as 2 and you write it as 2 square. Okay. So, this is like 1 upon 4 into 1 upon cosine hyperbolic of beta e j minus mu over 2 the whole square. Okay. So, this is basically you can write it as maybe 1 upon 4 a second hyperbolic beta e j minus mu by 2 the whole to the power square. So, 1 by cos hyperbolic is second hyperbolic, and you know that so this was, let us not forget the site that this was the second cumulant. Now, you have it in terms of energy. So, if you know the plot of cosine hyperbolic, you know how second hyperbolic would look like. So, cosine hyperbolic is has a plot of something like this. So, if you plot cosine hyperbolic as a function of x, then it will have a minimum at x equals to 0, where this will be 1 and then it will go to infinity, because cosine hyperbolic has well, you already know by now, but I am just writing it for reference. So, at large x it behaves like an exponential, and for negative large x also it behaves like a positive exponential. So, it goes to positive infinity as x goes to. So, definitely second hyperbolic has to now its maximum value has to be 1, and then it should go to 0. I am not a very good artist, so please bear with me if you can draw it better than me. So, I know I have to just make the infinity go to 0. Okay. Please draw better than me. This is second hyperbolic, because when cos hyperbolic goes to infinity, it will go to 0. And second hyperbolic square will go even faster than second hyperbolic. So, this would be much faster, it will go to 0, but you already know that it goes to 0 when x is so it is maximum, second hyperbolic is maximum when x is 0, and our x is actually beta e minus mu, which means if I want to plot if I want to plot beta E j versus the fluctuation, then I expect the fluctuation to be maximum at beta mu, and this is where I will have this passing from 1 and it will quickly go to 0 on both sides. So, when E j becomes mu, you will have a maximum fluctuation, because that is where second hyperbolic 1 becomes 1. So, that is where the fluctuation is maximum, and away from it the fluctuation will go to 0 rapidly. If mu was 0, then this shift in peak would come back to 0, but mu is not 0, and so you have a maximum fluctuation near near the Fermi surface. Which is what you expect, because if you look at your distribution function, this was at t equal to 0, but so this is at t equal to 0, and if you want to sketch for distribution for non-zero temperature, then this is would we expect the maximum fluctuation to be at close to the Fermi surface, which is somewhere here. And that is precisely what you get here. Here. So, I will take this as some mu at t equals to 0. Okay. So, this completes the discussion on the fluctuations, and I think you are now in a position to do most of the problems that are of physical relevance across the 3 chapters, and if there are any concerns regarding these problems, you feel free to write to us through the Google form that has been uploaded already, and we will be very happy to discuss issues across the chapters in the live session that is going to come up in the next week. So, please write to us and talk to my TA in the chat rooms, and we will get back to you as soon as possible, the fastest possible time scale. Okay. So, thank you very much. Thanks for your patience. We wish you all the best for your exams, upcoming exams. If there is anything we can do, we can fix online, just let us know, we will try to do our best.